Hope you're having a good week, good start to your week. It's Friday here on this side of the video, so that's exciting. We got the weekend ahead. This video will be kicking off Unit 2. Okay, Unit 2 is all about fossils, fossil evidence, um, and I see some typos on there. That's not good. But fossil evidence, and then we're going to talk about the geologic time scale, which is basically um, an entire scale of Earth's history from what we know, what we have found from the rock layers, okay, and fossil evidence as well. So getting started, this is the standard we're unpacking is 2-7 and talking about how our systems change Earth's surface over time. We're going to talk a lot about this one as we move into plate tectonics in the next unit. So at the end of this lesson, you should be able to identify how rocks and fossil evidence tell us how Earth has changed over time. We're going to start with James Hutton, the father of modern geology, is what people would call him. This was a brilliant physician, went to school to be a physician and a naturalist physician at that. And then decided to take a break and farm. And so left Scotland and went to London and began a farm. And so a lot of what he found, a lot of what he observed, very observant man, um, really laid the foundation for modern geology. Okay, so they do call him the father of geology. Uniformitarianism is a phrase that came about a little bit after Hutton, but Hutton again laid the foundation for that. The term uniformitarianism, and I know it's a hard one, is basically it means the processes that are at work today, the processes that we see, the processes that we talked about with the rock cycle, earthquakes, volcanoes, all those processes are the same processes that have always occurred on Earth, always helped shape Earth's surface. And then those are also the processes that are going to continue even after we don't even exist. So as long as Earth exists, these processes have continued to occur. Again, some of those are volcanoes, erosion, ocean waves, earthquakes. Um, Hutt did discover that these processes are slow, and some evidence that he used interior Earth being molten material, which was not a well known or well accepted theory at that time, but talking about how internal Earth is moving and it's shifting rocks that are on top. So, it, again, wasn't widely accepted at the time because most people during that time frame believed that the Earth was only about 6,000 years old, and to to talk about having molten material and those rocks being recycled on the crust would mean that Earth was much older than that 6,000 year period. So the first evidence that we're going to talk about here is rocks. And I'm going to switch gears and go over. We are going to do Pangea. There you go. We're going to do this lab in class and we're going to walk through it bits and pieces. But I just want you to take a look at this. It'll give you a good visual. We can move these continents around. You can go ahead and play with this before you get to class if you'd like. I have it already assigned for you. But you can move these continents around and you can see how the rock evidence here, 2 billion-year-old rock, similar in South America as in Africa. And then you can see 450 million-year-old rock on our East Coast and then also over here on the other side. So you can see how these things match up or line up. You probably already had a sense of that just looking at the coastlines here, that these pieces kind of match up like a puzzle piece. So there's a good visual for you. All right. Geologic history is preserved in the rocks. Here's an example. This limestone right here, we've talked about limestone before. We talked about that last week. Used to be a coral reef. How did it go from one to the other? Well, time, plate tectonics. We'll get into that next. Sandstone from a sandbank. You can see that here. I also had pulled up the Grand Canyon in class last week so we could look at some of those sedimentary rock layers. That's another great example. Again, a 2,000-foot elevation tectonic plate shift is what gave us this beautiful natural landmark called the Grand Canyon. The layers have relationships, and we again the law of superposition. We're going to talk about that coming up, and we're going to dig deeper into Earth's layers. So I'm not going to get into that right now. But by examining the boundaries between these rocks, again, we're going to do this with Interpreting Geology Lab, and looking at a cross section of those layers. I don't have that handy really quick, but I probably could find one cross section. Google go of not layers of skin. Here's an example. I got a couple things pulled up here. But looking at the boundaries between where these layers are gives us a lot of information about what happened during that time frame. So again, there are relationships between those rock layers, and that gives us a lot of information. Um, where you might see, and a lot of people, this might be easier for you. If you think about a tree, a cross section of a tree, you know how a tree has rings, right? Well, you can tell where there were periods of drought, and you can tell where there's periods of a lot of rain because the rings will be larger or smaller, consistent with that of drought or a lot of rain. And so rock layers are kind of the same thing. You can see where erosion has occurred, and you can see how much erosion. You can see where there's been shifts in the plate tectonics. So we're going to be looking at that next week, but go ahead and get that idea that we are examining those boundaries between the rock layers to help us determine what happened. All right, now to the nitty gritty fossil evidence. I know y'all are super excited for this. Fossil evidence is the other type. We're going to look at that with Pangea. So I'm going to flip back over here. So there's the rock layers. And here's some fossil evidence. And we're going to play around with this, try to fit those together based on both of these concepts here. But again, the fossil evidence, they didn't hitch a ride on a boat, right? These creatures, these organisms didn't swim that far. So how did we find these fossils in the same location across the Atlantic Ocean? So keep that in mind. Back over here. I know I'm switching around a lot today. Sorry, guys. All right. Suppose you're examining an area of rock, and you find, let's say, a layer of shell, and then several fern-like plants in that shell, that rock. Okay, we know that ferns live in warm, humid environments, not dry. Um, but let's say we found it at the top of a mountain. What could we conclude from that? Um, other examples would be in Antarctica. If you found fossils in Antarctica where we know there's no trees, right? If you found tree evidence, fossil evidence of trees in Antarctica, what could you conclude? Or how about Himalayas? They're the tallest mountain range in the world. So we have found seashell fossil evidence at the top of the Himalayas. Why would that be? Why would that happen? Why would that occur? So as you start thinking along that path, you're thinking like James Hutton. Why would that be the case? All right, so using animal fossils and plants, that really should say plants, using any kind of fossils, really, we can roughly estimate the age and the history of an area. This is an index fossil, and probably the most common index fossil that is used is the trilobite. Why? Because it lived for a long period of time, but its layers of evolution were vast. And you can see down here, it began very small, it's very simple, and that is so important. That concept I just said right there starts very small and very simple and becomes something very complex. And that is the running theme for this entire unit. Begins small and then becomes more complex as time marches on. So an index, just like an index you would use in a book, right? It's your reference, it's your guide. So this is a fossil that we use as a guide to determine the relative age of the things around it. So if we find a trilobite that is, let's see, 400 million years old. Okay, we know if we find that in a layer, we know that that layer is around 400 million years old. And then we know that everything above it is going to be slightly younger, and everything below it is going to be slightly older. So this index fossil gives us a way of determining relative age, not exact or absolute. We'll talk about that too, but gives us a way to determine the age of the things around it. Okay. Trilobites, of course, lived during the Paleozoic era, the age of marine life, where everything existed in the water, and they were so widespread that we can use these to determine relative age of organisms or fossils or rocks over a large geographic area. Now I'm going to talk about the individual types of fossils here. This first one is called petrified. Petrified. When you hear that word, normally you think scared to death, right? I want you to think of, when you hear the word petrified, when you hear petrified fossil, I want you to think of Medusa. We know that Medusa turns her victims to stone, right? Got all the snakes coming out of her head and turns her victims to stone. And that's what happens here. No, it's not, the rock's not scared to death, or the tree's not scared to death and turns into a rock. But what happens in dry, very dry, arid climates, you know how here everything it starts to decay pretty rapidly because we have a lot of moisture in the air. Um, in dry, arid climates, that's not the case. And so the minerals themselves actually come in and replace the parts of the organism, the tree typically is what you're going to see, and it turns it to stone. So it is actually not the tree anymore. It is a rock. And here's some examples. Again, this is a dry, arid climate. You can see here's a petrified tree. We have an entire petrified forest. I do believe it's a national, sorry, forest. Okay, so it's just that one there. There's a petrified tree. Here's another example right there. Oop, go back. Again, so dry, arid climates, the organism itself is replaced by mineral and sediment, causing it to turn to stone. So think Medusa. The next one's like the yin and the yang, the ball and the glove. All right, these two go together. They form together. They're called mold and cast, and kids miss this all year. So pay attention here. Mold and cast form when a shell or something like that is buried in sediment. Okay, the sediment fills the inside and it covers the outside, and the material inside decays. Okay, the organic material is going to decay, but what it leaves is an impression and a replica. And I need you to understand the difference between those two, because when I say cast, most kids are like, oh yeah, like a cast that goes around your arm. No, 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 no. That's the wrong idea. If you answer like that, then you're going to get it wrong every single time. And if you get it wrong once, you get two of them wrong, because you'll get mold wrong as well. Think of it like this. You go into the dentist, a lot of us have probably had braces. You go into the dentist and they put that big old thing in your mouth and you have to bite down on it. And then they put that nasty little suction cup in your mouth that makes all the weird noises and gets stuck on your tongue. Ugh, I hate it. Anyways, so you go in, you have this impression done. That is the mold of your teeth. They then fill that mold with some kind of casting material, okay? And as it hardens, an exact replica of your mouth. A student actually brought me one of these. I kid you not, y'all. Brought me the replica of her mouth, but to show the difference between mold and cast. So that's pretty funny time. So mold again is that impression of it's here on the left. If you're looking at the Nearpod, here on the left is that impression that's left behind. Then we have on the right what filled the inside before it decayed, and that is the cast. Okay, so think about it not like a cast that goes on your arm, but maybe like a molden cast of your teeth. This one's pretty interesting, and I know I'm going to date myself here, but when we were kids, we used to have this paper. We put like pennies and stuff under it, and you run a pencil across the top, and it would kind of give you this picture of the penny. Um, Carbon paper. That's what we used to play around with stuff like that. But a carbonized fossil is just a picture. It's just a carbon imprint, usually like delicate plants, can be fish as well. We see some of those, but that they die and sink down to the bottom, get stuck in that mud, and layer upon layer of mud packs on top. Eventually, the mud hardens. Okay, it starts going through that sedimentary rock process, and all the dead decay material goes away, leaving a picture, a carbon imprint. And this one is the easiest one to get because if you see a test question, it's asking about fossils and it says carbon, the answer is carbonized fossil. Trace fossil. This is everybody's favorite. Trace, just like trace evidence. If you watch crime shows, the perpetrator left trace evidence behind. That's how they found who it was. Trace evidence can be anything that is left behind. No part of the organism remains. No part of the organism is there or was ever there. So this is something left behind. So could be tracks, could be burrows. I could show some pictures of that. I'll do that in class. Or it could be feces. Yeah, so you can actually get some fossilized dinosaur poop. I don't know if you guys have ever been to Gatlinburg, Tennessee, but they have a store there that sells fossilized dinosaur poop, if that's what you're into. And then we have preserved. Okay, preserved, and I need you to get this, so pay attention. Perk back up. Preserved is the only type of fossil we can extract DNA from. So you see that the creature is wholly preserved in that amber or tar or ice, okay? Just like we found woolly mammoth um, wholly preserved in a glacier not too long ago, a couple of years ago. They did get to extract the DNA, and they are still working on pairing that with elephant DNA because we didn't learn our lesson from all the Jurassic Park movies. So hopefully that doesn't work out. But preserved, just like you can remember this, maybe if maybe some of your parents or your grandparents preserve food, they might can or jar some of that food that they have made and put it up. That preservation, there you go, sorry, of that material is what we're talking about here. So it's wholly preserved, the whole thing is intact and it is there. Again, this is a key question I see pop up a lot on tests and quizzes. Which one can you extract DNA from? The answer is preserved. Okay. All right. What do fossils do for us? They give us data about ancient climates, indirect evidence of past life, meaning like trace evidence, right? How they lived, where they lived, what they ate, those kind of things. Then they give us direct evidence of past life, being the organism themselves, and especially like preserved fossils. Um, they also tell us about reasons for extinction, why some things cease to exist. Could be climate change, could be meteor impacts. We know that from the dinosaurs. Again, we're going to talk about that more in the next lecture. And then evidence for continental drift, just like I showed you that picture of Pangaea. Provides us, the fossil evidence provides us with lots of evidence on how the Earth looked at certain points in time. All right, guys, I think that's it. I hope you got some notes. See you guys next week. Have a good weekend.